Okay, I think it's 9 o'clock, so I think we can begin. Dr. Udick, if you want to read your script. I think all the committee members are here.
Awesome. Well, thank you all for coming. Good morning and welcome to the Dissertation Defense. My name's Steve Udick and I'm the graduate faculty representative for this defense. This means I'm not a voting member of the Defense Committee. Instead, I'm here to make sure the defense follows graduate college guidelines. So to begin, I'll ask everyone to silence your cell phones and other electronic devices. Probably not as appropriate for this one, but put yourself on mute if you're not actively speaking. So there's several parts of the defense. First, we'll have a presentation by Buchanan. At the end of the presentation, there'll be a time for members of the audience to ask questions. When the questions are done, I'll ask the audience to leave so the defense committee can have a private session with the student. And when that's done, we'll ask the student to leave so that the committee can discuss the defense. So with that as an introduction, I'd like to introduce Matt Cohn, who will introduce the student and the rest of the committee.
Hi, thanks, Steve. Well, it's a great pleasure to introduce Buchanan Kurzweil as today's candidate for his PhD defense. Buchanan got his undergraduate degree at Utah Valley University in 2015 and dove right into a PhD here at Boise State. And not only that, he dove right into a big project in the Alps, a multi-million-dollar project among lots of different universities. So he has been involved with lots and lots of research projects spanning everything to do with the Alps. One of the things that I particularly appreciate about you, Buchanan, is you are such a phenomenal programmer. You have done such amazing things with computational work in the geosciences. And for those of you who are unfamiliar with his capabilities, I think they'll be on fine display this morning for you, afternoon, evening for Philippe, and late night television for me. So Buchanan, why don't you take it away and introduce us to the beauties of the research you've been doing.
Well, wonderful, thank you, Matt, and everybody for joining us here today, especially those committee members who are abroad. Okay, you should all now be able to see my title slide and my cursor, I hope. Okay, so I had a hard time titling this work. You may notice that I chose to study 3 different topics. First is surface heat flow and the metamorphic rock record, and also subduction geodynamics. And I realized, like Matt mentioned, the common thread that ties my dissertation together is my approach to understanding these problems, which are using a variety of computational techniques, which we'll get at today. So for my acknowledgements, I have several people I'd like to thank. First, my committee members, Drs. Matt Cohn, CJ Northrup, HP Marshall, and Dr. Stephen Udick, all representing Boise State University, and then Dr. Philippe Agard joining us from Sorbonne in Paris. I'd like to extend a very special thanks to Sarah Peniston-Dorland and Brain Feynman, who together with Matt Cohn are principal investigators on this large eFire project, which is funded by the NSF, which funded my research. So big thank you to them. Beyond the principal investigators, I'd also like to thank the eFire and Zooming in Between Plates participants. It's been such a pleasure and to get to know all of you and share some time out in the field with you and have many wonderful discussions about topics of alpine geology and subduction. Big thanks to Dr. Tar Skria and his students at ETH in Zurich for hosting me as an academic guest and for in very short order teaching me how to code and do numerical geodynamic modeling. And lastly, a special thanks to Philippe and his students at Sorbonne for hosting me in Paris and also for touring us around the Alps and showing us all of your amazing locations. To all my loved ones who support me in so many different ways, thank you very much. And also those who are not on this, there's two people who are on this slide, two groups of people who are on the slide. Those are the administrators of the geoscience department here who have done just a phenomenal job facilitating my research and many really difficult travel itineraries. And also the high performance computing team at Boise State deserves a shout out because I did a lot of work on their systems, and without their systems, I really wouldn't have been able to do what I'm about to show you. Okay, so in the next 45 minutes or so, I'm going to introduce you to subduction zones, what they are. Luckily, we only have to define a few terms to get ourselves started. Then I'm going to work our way through three really important observations that motivated my research. And then we're going to step through the body of the dissertation, which is itself is in three parts. So the first part, the first chapter, we'll look at numerical simulations of subduction zones. The second chapter is concerned with the distribution of heat flow on the globe near subduction zone segments. And the third chapter will trace and classify more than 1 million simulated rocks and then compare those to the available metamorphic rock record. And I'm going to, at the end, try to distill all of these details down into some digestible conclusions and takeaways. And then at the end, as Steve mentioned, there'll be some time for questions from the audience. So beginning with the most basic conceptual model of subduction. Subduction is a tectonic process that was discovered during the 60s, whereby oceanic plates that are formed at spreading centers in ocean basins are then consumed by subduction, where they sink and get recycled into the deep interior part of the Earth at convergent plate boundaries. This process of subduction is important for a variety of different reasons. It, on a large scale, is the major chemical differentiator between the Earth's surface and its deep interior. And also from a hazards perspective, it triggers some of the most consequential natural hazards like large megathrust earthquakes and also explosive volcanism. So just to define a few terms here, you'll hear me refer to the slab. And by that, I just mean the subducting oceanic plate. There's a few things important to note about the slab. The first is how fast it's moving. So its convergence velocity or subduction velocity. Also its age, which is related to the thickness of the slab. And then we have this thing called the thermal parameter, which is always notated with the Greek letter phi. And the thermal parameter is simply the product between the subduction velocity and the slab age. And it's kind of a funny unit, and it's meant to capture sort of the thermal and kinematic characteristics of a subduction zone. So it's not necessarily the most intuitive parameter, but nonetheless, it's often used to compare and characterize subduction zones. So it's important just to keep in your head that phi is the product of the subduction velocity and the age. Now moving to the upper plate, we define in our work the thickness of the upper plate. We use this notation Z1100, so you'll see this. You don't really need to know what the 1100 means, just understand that Z1100 refers to the thickness of the upper plate, which in our case is always continental. The region of mantle between the upper plate and the subducting plate is called the mantle wedge. And we have really good reason to believe that at some point along the top of the top of the subducting slab starts to exert significant drag forces on the mantle wedge, which then induces what we call mantle wedge circulation. And this point at which the slab begins to mechanically couple and exert significant drag forces on the mantle wedge is what we're defining as the coupling depth. And we use the notation Z sub C. There's one more term here that you'll hear me use a lot. It's the slab mantle interface, or just simply the interface. like the vast majority of subduction zone research is focused on this region because this is where the seismic cycles are happening. This is where mass and a lot of energy transfer is occurring. And so when I refer to the interface, I'm just talking about the narrow region between the two plates. Okay. So with those, like some sort of basic understanding of the structure of subduction zones and some of the key terms, we now jump to a much more updated, modern, recently published conceptual model of what subduction may have looked like some 40 million years ago between Europe and Africa. Now, ultimately, this subduction zone led to a collision between the two continents and the building of the Alpine mountain belt as we know it today. And I just want to, for a moment, draw your attention to the very western part of this subduction system, where you see we have these little slivers of blue and orange material. These represent fragments of crust and sediments that don't get successfully subducted. Rather, they, at some depth, get detached from the downgoing slab and sort of safely move to the upper plate. We call this rock recovery, or I refer to this as rock recovery. And if you look at how this figure is drawn, you'll notice that there seems to be some interpretation of different detachment depths changing along strike. And I think what this figure beautifully illustrates is two of the really key questions that are actively being researched in the field today, which are, from which depths do rocks get recovered? How are rocks distributed in terms of depth, and also how many rocks get recovered from which depths? And then how exactly is coupling distributed along a subduction interface, and what is its relationship to recovering material from the downgoing slab, if any relationship exists? So these are important questions. There's been a significant amount of work done to try to answer these questions. And next, I'm going to just, I feel ashamed not summarizing so much work, but I'm going to focus just on three key observations that motivated my own research. The first comes from a paper published by Watt and Wong in 2009, where they use 4-arc heat flow to invert for coupling depth. So it's useful to just quickly step through how they did this. First, they simulated subduction zones in Northeast Japan and a bunch of other subduction zone segments. Hopefully you'll recognize that the bottom of these panels are numerical simulation of the subduction zone, where we have a converging oceanic plate coming in from the left down to the right. Now in these models, what you can do is you can calculate the simulated surface heat flow. And you can also adjust coupling depth by adjusting the length of this light blue layer, which represents just a low viscosity layer that's numerically implemented to control coupling. So now we have this sort of a knob that we can tune. We can adjust coupling up and down by changing this blue layer. And when you adjust coupling, you get a response from surface heat flow. And the red data points represent actual heat flow measurements that were taken along a transect near Northeast Japan. And what they find is that when you tune the coupling knob to about 75, 80 kilometers depth, you get the best fit with the empirical data. Now, it turns out that most models also fit within a narrow range of coupling depths that center around 80 kilometers or so, despite very different boundary conditions in terms of slab ages, convergence velocities, and thermal parameters. So this is really curious and leads to the question is like, what controls coupling depth? If none of the if slab age, convergence velocity, and thermal parameter don't seem to have much of an effect, like what does affect coupling depths? Okay, this is the first question that I try to address in my dissertation. The next two observations both come from compilations of the metamorphic rock record. So on the right diagram, you're seeing a pressure temperature diagram where we have temperature on the x-axis and pressure on the y-axis, and all of the individual data points on here represent individual rocks that were sampled from some subduction zone, fossil subduction zone around the world. where we've used a technique called thermal barometry to estimate the maximum temperatures and pressures experienced by those rocks during subduction. And what we notice is that some of these rocks tend to follow along trends in PT space. And let me just draw your attention to the plot on the left where I've drawn just schematically some different thermal gradients. So lines on here in PT space represent thermal gradients. And you may notice that the kind of bold and colored circles, those are rocks that were sampled in the Alps, in the central and western and eastern Alps. And they tend to fall along like an intermediate thermal gradient, like this yellow line to the left. So rocks that fall along warmer trends experience more rapid increase in temperature as they go down the interface. And then rocks can follow colder trends as well. So what has been observed is that if you notice this blue region, now I've drawn in PT space, this is the region that envelops most thermal gradients predicted by numerical models of subduction. And what has been noted by some is that it doesn't really overlap with the vast majority of the distribution of the metamorphic rock record, except for the lowest phi simulations, or those subduction simulations with the youngest oceanic plates and or the slowest convergence velocities. So the observation is, well, the PT estimates from the rock record are mostly inconsistent with thermal gradients predicted by this particular set of numerical models from Syracuse and other, except for, like I mentioned, the lowest phi models, which is also curious and led me to question how do recovery rates change with these boundary conditions, age, convergence velocity, and thermal parameter. So for example, if rocks are recovered at higher rates from these low phi systems, they might be overrepresented in the rock record and therefore be contributing to this sort of inherent or apparent bias. And also just in general, how do recovery rates change with the other important parameters that we've discussed? This is the second question I'm addressing in my dissertation. And then the final question comes from this observation, still from the compilation of PT estimates from the rock record. Now we're looking at the cumulative probability of recovering rocks from certain depths. So on the y-axis, we still have pressure, and on the x-axis, we have the relative proportion of rocks. And if you draw the cumulative probability curve for the rock record, you get this white curve, which tells us that more than 80% of rocks are recovered from depths of less than about 2.4 gigapascals. And further, the lack of curvature in this white curve in this region here suggests that recovery of rocks from all these depths is basically equally likely. Whereas recovery of rocks from depths beyond 2.4 gigapascals becomes increasingly rare, and these rocks constitute just a few percentage of the available metamorphic rock record. Now, it didn't need to be like that. We could have had a rock record that had a bimodal distribution where we have lots of rocks getting recovered from low pressures, and then sort of a gap in the middle where we don't recover any rocks, and then recover rocks again above 1.5 gigapascals with regular regular intervals. Or we could have had a rock record where we mostly recover low pressure rocks, but with a few eclogites or a few really high pressure rocks. Or we could have had a curve that looked something like this, where 100% of rocks are recovered from less than a gigapascal and we don't have any eclogites. But we don't have the brown or the yellow or the green curve. What the rock record shows is the white curve. And so the observation is rocks recovered from about 0.8 to 2.4 gigapascals make up 80% of the rock record, and they are all equally represented. So my question is, how do recovery depths change with age, convergence velocity, and thermal parameter? In other words, can we reproduce the white curve first of all, or does the curve look more like the green or the yellow or the brown in simulations of subduction zones? Okay, so just in summary, here are the three questions that I'm going to address now in the body of the dissertation. First, what controls coupling depths? And then how do recovery rates and recovery depths change with these subduction zone boundary conditions? here's how we're going to do that. So the first two chapters are focused on the first question, and the last chapter's focused on the last two questions. And I just want to pause to note here that there's been a tremendous effort to try to understand these things. And the reason why these problems are so difficult is because we don't really have any means of directly observing any of these processes because they're operating at such depths. And so we rely on indirect observations like heat flow and the metamorphic rock record, which are really like riddled with complexity and obfuscated by noise. And it's like really, really challenging to do this. Another method that I have employed in my own research over and over again is numerical geodynamic modeling. So these are physics-based simulations, which you're seeing in the bottom here, that are governed by physical conservative laws. That is conservation of mass, conservation of momentum, and conservation of energy. Now, if you solve these equations, given some assumptions for material strengths of rocks and also some boundary conditions, we can simulate natural buoyancy-driven plate motions. So in the first chapter, I set up 64 of these simulations with different thermal parameters and different upper plate thicknesses. We run these things for like 10 million years, and then we observe the coupling depths. We then fit a linear, a model that predicts coupling depth based on estimates for the upper plate thickness and thermal parameter. And then we take that model and then we predict coupling depths for modern subduction zones. And what we find is that coupling, the depth of coupling, is primarily controlled by the upper plate thickness and and the thermal parameter has a very, very small, almost negligible effect. Now in our models, coupling itself is implemented by formation and dehydration of serpentine in the mantle wedge, which is this reaction here after Schmidt and Pauli, where you have this weak ultramafic mineral serpentine transforming to form, breaking down to form orthopyroxene, olivine, and releasing some water during that reaction. Now, I'll spare you the details of numerically implementing a metamorphic reaction in a model like this. You just need to understand that where we have serpentine forming at the interface, which you can see is this pink layer at the top of the plot, we have effective decoupling, or the plates are allowed to slide past each other. And then where serpentine breaks down, there's this sort of abrupt viscosity change, which you can see at the bottom of the figure here. And that's where we observe coupling occurring. And so observing coupling is as simple as visualizing the rock type and visualizing viscosity and figuring out where the serpentine layer kind of terminates. So here are the observed coupling depths for all of the 64 simulations. The gray scale represents the coupling depth. So there are 64 squares here. Lighter squares represent shallower coupling and darker squares represent deeper coupling. Along the x-axis is increasing thermal parameter, and increasing from top to bottom on the y-axis is upper plate thickness. And so if you just look at this for a moment, you can probably already start to see some correlations here. For example, if you just scan your eyes left to right, you might be able to distinguish like a slight lightening of the squares going from left to right. This is indicating that there is a very, very weak effect of thermal parameter on coupling depth. However, if you scan your eyes, pick any column and just go from top to bottom, you'll see a systematic darkening or systematic increase in coupling depth with increasing increasing upper plate thickness. This is really the key result of this study, that coupling is insensitive to thermal parameter, but it has a very strong response when you increase the thickness of the upper plate lithosphere. So we've observed coupling depth for 64 simulations. We've regressed this model that predicts coupling depth, represented here as this contoured surface. The black squares represent all of the numerical models where we've observed coupling depth. And now it turns out we know phi for most modern subduction zones. And we can actually invert for lithospheric thickness using average upper plate surface heat flow, which from the literature has been estimated for 17 subduction zones. And so I've gone ahead and just done that conversion, the inversion to estimate the upper plate thickness for these subduction zones, and then just plug them into the model and just see what the predicted coupling depths are, which is where they land on this contoured surface. And what we find is coupling depths span, they center right around 80 kilometers depth for these modern day subduction zones, plus or minus about 20 kilometers or so. And we get the same result despite the exact form of the regression that we use, be it a linear or a polynomial form. And so what does this mean? Well, if you're asking how similar are coupling depths, understanding that there's a really strong relationship between upper plate thickness and coupling depth, the question in my mind should be rephrased as how similar are upper plates in terms of their thickness? For example, it's possible to have common coupling depths among different subduction zones if upper plate thickness is a constant. Now, it might seem like really highly unlikely that upper plate thicknesses for all of these different subduction zones are comparable, but in 2006, Curie and Heinemann sampled heat flow well into the upper plate for several subduction zones. And what they find was surface heat flow profiles that showed consistently high heat flow well into the upper plate. And they interpret this to mean that there is some uniformity in the thickness of our upper plates sort of globally, where upper plates are universally thin, relatively thin. Now, this jives like really well with this idea of common coupling depths in subduction zones, considering the relationship between upper plate thickness and coupling depth. However, when I looked into this for my by plotting up the newest, latest, greatest heat flow database published in 2019 by Lucas O, I immediately found a pretty glaring and well, there's a problem with this idea. And that is this: if you take transects from the same subduction zone segments that Curie and Heinemann did, but you take them in different locations, what you find is that some of the heat flow profiles are comparable and some of the heat flow profiles are not. So for example, if you go all the way to the east and you look at the heat flow profile along this yellow transect, what you find is well into the upper plate, you do not predict high heat flow, but rather there's low heat flow, which would imply a thick plate, not a thin plate. So really understanding whether or not upper plate thicknesses are a constant within or among subduction zones requires us to fill in the gaps. Like we really need a two-dimensional picture of the distribution of heat flow, which leads us to chapter 2, where we project surface heat flow onto the globe from the latest global surface heat flow data set. We then interpolate this heat flow in 2 dimensions using methods of kriging, and then we compare these kriging predictions to another method of interpolation called the similarity method. And I'll talk about the differences between the two in a moment, but what we find is inconsistent patterns of heat flow within and among subduction zone segments. So this would seem to go against this idea that the upper plate thickness is a constant among subduction zones. So the plot at the bottom is an example of the difference in these two methods. So we're looking here at a map view of the Central American subduction system, where you can see from the similarity prediction, it's really obvious to make out the Galapagos triple junction, where we have 3 spreading centers all converging, forming the Cocos plate, which is being subducted underneath Central America to the northeast. What you don't see in the kriging prediction is the Galapagos triple junction or any of the spreading centers. And the reason is because there's not a lot of heat flow data that have been measured there. So when you take the difference between the two, you'll notice that there's stark contrast in the southwest, where we have this different tectonic regime operating, than to this northeast, where the differences are actually really quite small. And just note that into the northeast, this is now we're into the upper plate here. So while there are really large differences in the Kriging and similarity predictions in certain tectonic regimes, in other tectonic regimes, they seem to have good agreement. Now, the different predictions come from different frameworks used to do the predictions. So Kriging itself is based on the first law of geography, which states that everything is related, but near things are more related. So if I were to take a heat flow measurement here, and then if I were to take a heat flow measurement 1 meter away, I would expect those heat flow measurements to be quite similar than if I were to take a heat flow measurement here and then one in Kansas. If those heat flow measurements were similar, it would be probably coincidental. However, and then compared to similarity, which is based on the third law of geography, which states that the more similar the geographic configuration of 2 points, the more similar their values. So what that means is, like, if I take a heat flow measurement and I know I'm right next to a hot spring, I expect the value of that heat flow measurement to be pretty similar to values of measurements taken near other hot springs, whether those hot springs were here or in Istanbul. Okay, so the space between points, or the actual geographic location between points for similarity, holds no bearing. It's all about respecting the lithologic and tectonic sort of configuration of that point in space. The differences themselves between the predictions are really difficult to interpret. For example, we see some subduction zone segments like here, Conchaca Marianas, which the differences between the two, they center around 0 and they have a relatively narrow distribution with shorter tails to either side than the rest. And then we have systems like Scotia and Tonga, New Zealand, which are clearly and significantly biased in one direction, and they have lumpy tails and long tails. And the differences in these tails is encoding something about the geodynamics and something about the differences in the frameworks that these predictions are based on. However, it's not really easy. It's not really easy to pick apart the pieces. Further, what we find is qualitative evidence that the spatial patterns of heat flow near subduction zone segments are inconsistent and therefore do not imply constant upper plate thicknesses, but still the picture is pretty fuzzy. And it's because even though there are some 70,000, 80,000 data points in this data set, it's relative to the space, it's still considered pretty sparse. And so whether you're using the Kriging prediction or the similarity prediction, in either case, it's still drawing kind of a fuzzy picture. Now, I believe that these methods have a great deal of promise to be used in the future to advance subduction zone research, not only because the accuracy and confidence of these interpolations are going to improve as the data set scales, but also because I think there's some improvements to the methods that can be made. For example, using a layered approach where you take a Kriging prediction as sort of layer 0, which is respecting the spatial continuity of measurements. And then you're updating those Kriging weights by bringing in geologic information, much like the similarity prediction uses. So combining those two together may give us a more accurate picture of the distribution of heat flow, and therefore could be more useful for subduction zone research. So finally, in chapter 3, we go back to those same numerical simulations of subduction zones that we used in chapter 1, but this time what we do is we trace these individual parcels of rock as these models evolve. And tracing these little parcels of rock as they move throughout this fluid is what you're seeing in this video in the center, essentially. I refer to these little discrete parcels of rock as markers. So I'll just call them markers. What we do is we trace a bunch of these markers, and then what we want to know is which ones don't get subducted. And so we apply a classification algorithm that basically the computer learns how to recognize which of these parcels or which of these markers are not getting subducted and which of them are getting recovered. So in the video that you're seeing, clearly the blue markers here, it's like a bunch of different colored markers, but only the blue ones are not getting subducted. These are the recovered markers that we're then going to compare to the available metamorphic rock record as if they were like subducted rocks that then later got exhumed. Okay, what we find is a negative correlation between recovery rates and thermal parameter. So the relative proportion of rocks that get recovered versus get subducted does seem to change depending on thermal parameter. And also what we find is non-uniform recovery of markers with respect to pressure, which means that markers are not getting recovered sort of all along the interface, but rather they're getting recovered in discrete regions of depths or regions of pressures. So for example, we see a really strong effect on the distribution of recovered markers with convergence velocity, with changing convergence velocity. So what these plots are showing is pressure, temperature, space. And the gray shaded contours here represent the distribution of markers, simulated markers that got recovered from these simulations. And just like a topographic map, the lighter contours represent peaks, and these peaks represent areas in PT space, regions in PT space where we get much more markers recovered than the darker gray shaded regions where there are fewer and fewer markers getting recovered. I should also note here that there's something like 300,000 or more markers that are basically bounded by these contours. So instead of plotting like 200,000 data points on here, it's much easier to represent this in terms of density, probability density. That aside, what you'll notice here is that the distribution in terms of where it is in PT space and also the shape of the contours are changing as you increase convergence velocity. So the slowest converging simulations, which are the top left, they have a much more smoothly distributed, distribution of recovered markers, although they still have kind of a high peak in moderate to low pressure temperatures and sort of a slight hill to higher pressures. But in any case, we see this change as we increase convergence velocity, where the distribution becomes much more segregated, and also it kind of shifts towards warmer conditions as well. So adjusting the boundary conditions of the simulations is getting a response from where we're getting markers recovered and also how many markers are getting recovered from where. Okay. We also observe the distribution of the recovered markers with respect to all of the other subduction parameters we talked about: age, convergence velocity, thermal parameter, and upper plate thickness. And just to summarize this figure for you, what we find is that pretty much for all 64 simulations, we don't reproduce a cumulative probability curve that looks like the metamorphic rock record. So for example, in the top left plot, the jagged black curve sort of in the background, that is the cumulative probability curve for the rock record that we saw before. And notice that only the yellow line, which is the most slowly converging models, even get close to reproducing the curve that we see from the rock record. And none of the other models, changing all the other parameters, all had pretty small effects. And so what we take away from this is that simulations are seemingly not recovering nearly as many blue schists as are being represented in the metamorphic rock record. And with respect to recovery rates, we see a systematic change with respect to thermal parameter, but not with respect to upper plate thickness. So similar to the last plot, if you scan from left to right here, you can see that there's a decrease in recovery rate as you increase thermal parameter. And as you increase lithospheric thickness, recovery rates don't really change at all. So to conclude, try to distill all of these ideas into some takeaway points here. What controls coupling? This is a question that I tried to get at in my dissertation. Well, what we find is that coupling is much more sensitive to upper plate thickness than it is to thermal parameter. This is really a key result. What this means is that common coupling depths for subduction zones are possible if upper plate thickness is a constant. However, what we observe with respect to heat flow is inconsistent patterns when you interpolate it in 2 dimensions. And this suggests that the upper plate thickness is not constant within or among subduction zones. With respect to recovery rates and recovery depths, we find that recovery rates are inversely associated with thermal parameter, and they're not sensitive really at all to upper plate thickness. And recovery depths, we see pressure temperature distributions of recovered markers are much more sensitive to convergence rate than they are to age or upper plate thickness. And also we see that markers are non-uniformly recovered from distinct pressure regions, and that blue schist rocks are underrepresented in our models compared to the metamorphic rock record. And the last take-home message here that I'll note is that when compared to previous work that analyzes surface heat flow along transects, our analysis seems to suggest a much more diverse view of subduction zone geodynamics than previously implied. So with respect to recovery rates and depths of rock recovery, it seems that subduction zones are much more diverse than they are similar. And I really have strong faith that in continuing to scale and improve interpolation methods for heat flow is going to lead to a lot of advancement in the field. But that task in and of itself is quite a daunting one. And with that, I have nothing more to talk about. So thank you very much. And I think we have some time now for questions from the audience.
Nice job, Buchanan. Congratulations and great job.
Thanks, Sam.
I think we'll just let you field questions. Somebody wants to ask a question, please just feel free to call it out.
Chat's fine too. Audio's fine.
Can I ask a question?
Sure. Hi,
Nice
Carson.
job, Buchanan. That was really, really great. And I loved how you explained everything. It was really, really nice. So my question is related to the coupling depths and lithosphere thickness and how that relates to hazards at subduction zones. Do you know a bit about that, or like how this work could then better tell us what kinds of earthquakes we're seeing in these different subduction zones?
Oh, such a fantastic question. Yeah, it's still really not understood exactly what the role of this idea, what this coupling depth has to do with seismic cycles. So there's some evidence to suggest that coupling has something to do with rock recovery, and rock recovery itself has something, the way that rocks get recovered, detached from the slab, is by release of seismic energy along faults. And so there's like an inherent link there. But I would say our understanding of the two is pretty fuzzy at the moment. But yes, I think that is a very much a goal of subduction zone research as a field, to understand how coupling relates to seismic cycles and also how metamorphism might induce those types of things.
Thanks.
Mm-hmm.
I had a quick question. First of all, phenomenal job. That was really a joy to watch and to learn from. And you kind of talked a little bit about the challenges of trying to study something that's so physically inaccessible as a subduction zone. And so I was curious if you could kind of just stroll into a subduction zone and kind of collect one, either rock or some measurement. What do you think would sort of enrich these models that you've created the most, and why?
Oh, you should come to our closed door session. That's such a great question. We can learn a lot. We do learn a lot by looking at these rocks exposed in the field. For example, the only reason why I chose to implement coupling by way of this serpentine hydration dehydration reaction is because we see evidence everywhere in the Alps and other places that serpentine rocks are closely associated with rocks that get recovered from subduction zones. So when you go to these areas, although we can't, like fossil subduction zones are great areas which you're alluding to do this kind of work. In terms of like, are there specific observations that I would try to look for? They would be something along the lines of looking for evidence of exactly which metamorphic reactions are controlling coupling. So for my work, I chose to focus on serpentine for some reasons that I won't get into, but there are other dehydration reactions that might be causing similar phenomena or changes to viscosity in subduction zones. And so like taking kind of account of the relationships there, again, is a really difficult task. Matt was joking yesterday about we could go to somewhere like the Franciscan and just like literally collect rocks like every square, like every few meters, and then do thermal barometry and get a way bigger picture, but a better picture. I'm not sure if that any of that answered your question, but thanks, Molly.
Perfect, thank you.
Emmanuel, you have your hand up. I see you're the only one on my screen I can see.
Hi, Buchanan. Oh my God,
Hi.
congratulations.
Thank you.
I get teary-eyed on my side here because, you did a fantastic job in your presentation. So since you're already talking about serpentinites, obviously I'm going to be asking questions about serpentinites.
Yeah.
In relation to your chapter 3, because in chapter 3 you're doing this numerical modeling where you see certain rocks being exhumed, and so what caused them to be buoyant? Is that just density?
Good question. Yeah, it's a combination of density, density contrast between the mantle and serpentine. So yes, in the model, when these rocks kind of transform to make serpentine, their density does change, which then changes buoyancy forces.
So all those, sorry.
I was just going to say the other thing is there's like a real dynamic and kinematic reason too, because when you look at the models, there's the coupling depth. It kind of forms this region where you have weak serpentine kind of in this wedge shape here, and you have really strong stiff mantle here, and then obviously beneath you have the slab. And so anything that gets entrained in here, like if it gets detached to the slab and it makes its way here, it really is limited in the ways it can move. And so when it reaches this strong, stiff, cold part of the mantle wedge, it has really no choice but then to circulate back in here. So the distribution of serpentine, of course, is controlling a lot of this.
Awesome. So because that was what I wanted to ask. Like, so all those rocks that are exhumed have serpentine in it, or the serpentinites are still stable?
In the models, yeah, they're all surrounded. Okay. They're all completely enveloped in a lot of serpentine. Yeah.
Yeah, because I was just thinking that, along the slab mantle interface, when things started to break up and they become enclosed with serpentinites, even if you have like dense eclogite, but if you have like a block of eclogite that is surrounded by serpentinite, on itself, eclogite would not go up. But if you have like surrounding serpentinites, it will provide additional buoyancy. So in a way, the amount of the recovery rate might be affected by how much serpentine are present in the region, which is still, I don't know how, if it's how, like, I don't know the extent of serpentinization in there.
Yeah,
So
that's
I
another
was just thinking that,
PhD.
yeah, so I was just thinking that, you know, that the discrepancy in the models and what we see in rock record might be affected by how much serpentinites can actually be formed along the slab mountain interface.
Yes, of course. Yeah, great. Thank you for making that point. Yeah, I've had a lot of questions about exactly how much serpentine forms in these models.
Yeah.
And it's something that's worthwhile to like investigate the effects of all that stuff. Yeah.
Great job, Buchanan. Congratulations.
Thank you. At some point, we'll have to talk later because I have some cool pictures of diapirs that form in these things that I'd like to show you.
I like that. Thank you.
Yeah. Okay, I don't see any hands remaining. So are there any last questions anybody wants to slip in here before we go close door? If not, I would just like to thank everybody once again. It's really nice to see you all as well. I wish we could have done this. I could have done this in front of a live audience, but I'll take what I can get. Thank you guys.
Thanks everyone for coming.